Thank you. Bom dia a todos. Quero agradecer aos organizadores pelo convite, sempre um prazer voltar no Rio de Janeiro e no IMPA. Okay, that's the end of my Portuguese for today. Okay, so I'm going to talk about some work I did mainly with Daniel Hernandez Riperez about the, so to say, supersymmetric analog of the stack of stable maps. It was done in collaboration with Daniel, a little piece of it also in collaboration with Yuri Manin. And usually I start this kind of talks with a short introduction to supersymmetry, which is the physical motivation of supergeometry. So here now I have 2 or 3 slides, which I always use as an introduction to my talks in supergeometry. So some of you have already seen them. I apologize for that. So I think that the general framework we should refer to is one of the revolutions that took place in the 20th century in quantum field theory, namely in the description of the interactions among the constituents of matter. And that revolution was gauge theory, namely the realization that the interaction between the constituents of matter is a consequence of symmetries. So the fact that our universe has certain symmetries is equivalent to the fact that matter interacts with itself in a certain way, which means, for instance, that electromagnetism is a consequence of an invariance. Strong nuclear forces are consequences of another invariance, etc. Another thing which is very important, if we talk about the introduction of supersymmetry and supergeometry, is that the so-called elementary particles come in 2 flavors, 2 very general classes, bosons and fermions. To be a boson or to be a fermion means that the particle has a certain property, transformation property under the Lorentz group, or the Poincaré group, namely the group of symmetry of space-time, which also relates in a one-to-one way to the fact that this particle, from the point of view of the quantum theory, obeys a statistic, which may be the Fermi-Dirac statistics or the Bose-Einstein statistic. And the symmetries of gauge theory have the property that acting on a boson, they will produce bosons. Acting on fermions, they will produce fermions. But this, I'm not going into that because it's too complicated for a short introduction like this. But this immediately introduces an obstruction to the idea of obtaining a unified interaction of all, unified description, of all fundamental interactions, what is called the no-go theorem. And a way out to this no-go theorem was devised in the 70s, and that was the introduction of supersymmetry, namely of symmetries which mix, so to say, bosons with fermions. Transforming a boson, you may get a fermion, and vice versa. So these are a few names of the people who, in the 70s, introduced supersymmetry. And the second half of the slide is about a particular model which has a supersymmetry. It incorporates supersymmetry. So we have 3 fields. You see here phi and f are scalar fields, which basically means they are functions. And chi is a fermion. Geometrically, it means that it is a section of a spinor bundle. And then you see these are, well, infinitesimal form. Anyway, they are supersymmetry transformations. And you see that here the bosons are phi and f, and chi is the fermion. And you see that indeed this transformation acting on a fermion produce, on a boson produce a fermion, and vice versa in the second line. So this transformation really mixes bosons and fermions. And you may write for this field theory a Lagrangian, which happens to be invariant exactly. And I mean, the related action functional is invariant under these transformations. Actually, you may implement these supersymmetry transformations. I mean, they have geometric, mathematical consequences in two different directions. First, the very transformation I wrote here, they form not a Lie algebra, but a supersymmetric generalization of it, which is called a superalgebra. So if you see the first line here, the commutator, these are the translations. So this is, of course, an abelian Lie algebra, but then you may have an additional generator, which in some sense is an odd generator. And these, on one hand, commute with the translation, but they obey an anti-commuting relations in this way. And this odd part of the superalgebra closes over the translations. This is called the super Poincaré algebra. And there is a whole theory of these things. Superalgebras have been classified completely, generalizing Cartan's the classification of semi-simple Lie algebras. They have been completely classified basically by Victor Katz and other people of the Russian school. Basically, they gave a complete classification. Or you may think that, after all, since we have, you see, there is one point I didn't stress, but here there's a parameter in these transformations, which is this epsilon. You must think of this as a node parameter. So it will anti-commute with itself. It's not a commuting object. And then you may think that this means that you have to promote, for instance, usual spacetime by considering also some odd coordinates. So go into a new structure which has also, I mean, in addition to the usual coordinates x, it also has some odd coordinates theta. This was formally introduced by Salame Stratedi, I think, back in 1974, and then this gave rise to the notion of supermanifolds. Then mathematicians took this very seriously and started building a new theory, which is that we may call it a supergeometry. So a new geometric framework where, if we speak a coordinate language, we have, as I was saying, new variables, new coordinates that are odd in the sense that if you have a bunch of them, these will anti-commute among themselves. And the standard approach to this kind of geometries is the following. When you have, for instance, either a differentiable manifold or you have an algebraic variety, you have a topological space with a structure sheaf on it, which is clearly a sheaf of algebras over some field. And the idea to go to supergeometry is that you still have a topological space, perhaps with some additional structure, but then you have an enlarged structure sheaf where you also have odd generators. So there is an underlying ordinary geometry, and you build on top of it a supergeometry where you have an enlarged structure sheaf. Of course, this, from the point of view of scheme theory, is very natural. The only point is that the new structure sheaf will be a sheaf of graded anti-commuting algebras, not commutative algebras. And then, especially if you want to do this in algebraic geometry, actually you need to do quite a lot of work to generalize all the standard features of algebraic geometry. So this is something that I've been doing with other people, of course, but personally in collaboration with Daniel over the last, well, I worked in supergeometry many, many years ago, but then I stopped, and then I went back to it perhaps 6 years ago, and working actually in algebraic geometry. So we try to develop a kind of fundamental algebraic supergeometry. And this produced, for instance, these works. I don't want to spend time on that. So, basic object to do algebraic geometry is what one can call a superring. So this is a Z2 graded ring. And it's not commutative because what happens is that the element of the odd part, they anti-commute among themselves. Okay, so you have this commutation relation, right? The even elements commute with everything, and the odd elements anti-commute among themselves. And then you add a finiteness requirement. You want that the ideal generated by the odd elements is indeed finitely generated. And if you, well, of course, here we do already have here a ordinary commutative ring, which is the even part of the superring. But you can also get, in some sense, a smaller commutative ring just by modding out by the ideal generated by the odd elements.
Sorry, so the commutative part is not in the center. H0 is, so the element of H0 do not commute with the element of
They do. They do, it's written here. They commute with everything. The even elements commute with everything.
So what is A in AI and B in AJ? What does it mean?
If I is 0 and J is 1, the product is 0, so they commute.
Okay, thank you.
Okay, so the famous ordinary object or geometric object that underlies a supergeometry in this case is the spectrum of A. A is an ordinary commutative ring. You take the spectrum of it, and you have an affine scheme. And then on top of it, you define a sheaf of superrings, which is defined, if you want, in the usual way by localizing on the fundamental open subsets by localizing the ring. Okay? So in the natural way, this is a sheaf of superrings. An example is the affine superspace, where the superring is this one, no? Where K is any field, and the thetas anti-commute among themselves. They commute with the axis, and anti-commute among themselves. Okay, then you can define local ring superspaces, or you can define superschemes exactly in the same way, but working in this new category. You define morphisms absolutely in the same way. What is important to remember is that, for instance, when you have a morphism of superschemes, every superscheme, again, comes with an underlying ordinary scheme, which, using a physical terminology, we like to call the bosonic reduction of the superscheme. And then, for instance, if you have a morphism of superschemes, they will give it will contain the datum of scheme morphism between the underlying bosonic superschemes. Actually, when you have a superscheme, which is this calligraphic X, and the underlying bosonic scheme, there is a relation between the morphism between the structural sheaves, right? Because the structural sheaf of the underlying bosonic scheme is a quotient of the superstructural sheaf, so to say. This means that you may think that the bosonic underlying scheme as a closed embedding into the superscheme, and this is very useful thing to use in studying supergeometry. So something about the structure that these objects may have. So if we have a superscheme, and now this J is the Schiff version of the ideal J I introduced in a previous slide. So J is the Schiff generated by the odd sections of OX. And you take J mod J square. The result is an OX module, as a module over the usual structural sheaf. We call it E. Here you see the appearance of pi. Pi is the parity changing factor in the sense that J, in a natural way, is an odd object. Then the quotient, in a natural way, is an odd object. But I want to look at E as a usual coherent sheaf, so I decree it's even. So this means I apply the parity change factor pi. And then we say that X is projected if this morphism that I introduced in the previous slide here as a retraction. This is a particular case, which is kind of easier to understand, in the sense that you may ask the following. If you, let's assume that this sheaf E that we wrote here, which was born as a coherent OX module with X bosonic, let's assume it's locally free. And let's assume that the superstructural sheaf is actually the exterior algebra sheaf of it. And then if this is true, we say that the supermanifold is split. Of course, this immediately produces a recipe to build super schemes, because you can just start from a scheme and you specify a vector bundle on it, and you take its exterior algebra sheaf. And you decree that that is the sheaf of superrings. So this automatically, by definition, is split. No? So we have a split superschemes as a particular subcategory of the category of superscheme. A split superscheme is projected in a trivial way because this inclusion, you have this inclusion, right? Natural inclusion, the OX has the degree 0 part of the exterior algebra sheaf of E, and then this corresponds to the scheme, topological level, the scheme level corresponds to this retraction. So split implies projected. And of course, you may have a notion of locally split. So a superscheme is locally split if it is locally split. I mean, if it is split only locally. If this is true, if you call, of course, we have what we may call an even dimension, M here, which is just the dimension of the underlying bosonic scheme. And then under the hypothesis that X is locally split, you may call odd dimension of the superscheme the number of the rank of E. Okay, this N is the rank of E. And then you call it the odd dimension of the superscheme. There is a more general definition, which that doesn't require the superscheme to be split, namely you assume it is Noetherian, and then you define the odd dimension as the smallest integer such that the next power of the sheaf generated by the odd sections is 0. Okay, it's quite clear if you think, no, that J in the split case has exactly n generators which anti-commute. It's clear that locally split, in the locally split case, the two notions coincide, but the second is more general. So we shall stick with it. So examples. Well, clearly, what I said, you pick up a scheme and a vector bundle on it, and then you build the split superscheme associated with this data. And as an example of the example, you may think that, for instance, X, the underlying bosonic scheme, is a projective space, and you take n copies of the tautological line bundle on it, and you construct a super manifold, super scheme, sorry, out of it. definition of, this is the definition of projective superspace due to money. Automatically, the dimension, of course, is Mn, just by definition. Why not to consider super Grassmannians? Namely, you consider the graded module over K, Kmn, and you consider a space parametrizing the sub supermodules of it. So you have in a natural way this object, and this already is a non-trivial structure. You may prove that the underlying bosonic scheme is the product of two Grassmannians, right? Because you have Km, you have Kn, in a natural way you may consider the two Grassmannians. So this is the bosonic underlying scheme, product of two Grassmannians, and then you have some structure sheaf. And this actually, if you compute, this is locally split. You may prove it is locally split. And this is its dimension, even dimension, odd dimension. And you may see that the odd dimension indeed is the sum of the dimensions of these two Grassmannians. So it works. Particular case is the Grassmannian 1,0 of any superspace Kmn, and then you get, in an analogy with what happens in the usual geometry, you get a projective superspace. Now, of course, since we have a notion of projective superspace, you may think we have a notion of projectivity for a superscheme. No? A superscheme is projective simply if you can embed it into a projective superspace. And surprise, a super Grassmannian is not projective. It's been shown by Penkov, actually, and Skorniakov that unless the Grassmannian is trivial in some sense, which means that one of these numbers in this product is 0, it is not super projective. And you prove simply by first noting that if a superscheme is projected, the other definition I gave earlier, let's not confuse projective with projected. So if a superscheme is projected and the underlying bosonic scheme is projective, then the superscheme itself is projective. And then, since the super Grassmannian is not super projective, since the underlying ordinary scheme is projective, it cannot be, the super Grassmannian cannot be projected. Otherwise, it would be super projective, which is not. And therefore, we have an example of a superscheme which is locally split, not projective, not projected. Now, already with a Grassmannian, which seems to be a quite a natural object to introduce. Okay, again, when you do algebraic geometry, you need to consider properties of morphisms, and then these generalize in a rather obvious way.
Is there a notion of a fine superscheme, so an ideal inside the superalgebra?
Yeah. I mentioned it at the very beginning.
Okay.
Yeah, because, well, perhaps...
this is a sub-superscheme of the fine superscheme, or of the fine superspace?
Say it again, then probably I didn't understand. From the beginning, what did you ask from the beginning?
There is a notion of a fine superscheme.
Yeah.
And is this a super subscheme over super affine subspace? I don't know, of a fine superspace or not?
There are too many fine super.
AMN.
Yes, we do.
So an affine super scheme.
Yeah.
Subscheme. Okay.
Okay. Yeah. You were asking if there is a super version of the fact that an affine variety sits inside an affine space. Yeah, exactly. Now let's go to, I want to consider stable supermaps. So we start by telling what a supercurve is. And basically what I want to consider is a superscheme of dimension 1, well, I specified pure in the usual sense of algebraic geometry. Reduced here, we may simply mean that the underlying bosonic scheme is a reduced curve. And then in this case, you may prove that the structural sheaf is superstructural sheaf is necessarily of this form. It's necessarily of the form, the structural sheaf of the underlying curve, plus a coherent module of rank 1, which immediately implies that that a supercurve is automatically projected, no? Because you have automatically the retraction we were talking about. It may not be split in a rather artificial way if you want, but this is very useful because there is no need to assume that L is a line bundle. If it is, then by definition this will be split. If it is not, it's not split, but it will be projective. And then we have a notion of relative supercurve, no? Simply is a family of supercurves parameterized by a superscheme S. And then supersymmetric curves. One shouldn't think that just by considering something which is of dimension 1, 1, we have what in physics is considered to be the correct notion, correct generalization of an algebraic curve. This correct generalization is a supercurve which has an additional structure. Now, we should remember that this is, you see, this is the tangent sheaf of the supercurve. This has rank 1, 1. No? The rank is the dimension of the supercurve, which is 1, 1. And then we want to have a locally free subsheaf of rank 0, 1, so purely odd in a way, which is maximally non-integrable. Namely, if you consider the commutator of its section with themselves, and then in a natural way you go inside the tangent space, tangent bundle, the composition with the projection onto the quotient is an isomorphism. No? So this is not, this is maximally non-integrable, right? It would be integrable if the bracket was 0. And with this definition, it is as big as possible. Right? So it is maximally non-integrable. This is being called by physicists conformal superstructure. And actually, you can prove one thing, that you see we are working in a relative setting with the families. And so this is the base superscheme. It might be an ordinary scheme. Why not? An ordinary scheme is a particular case of superscheme. When this is true, when the parameter scheme is bosonic, then actually you may prove that the supersymmetric curve is just a spin curve. No? It's an ordinary curve with a choice of a square root of the canonical sheaf. So if you really want something new, which doesn't reduce to ordinary geometric structures, you have to assume that parameter space is a superscheme. It has some odd structure, so to say. And then you see, when you do, for instance, the modular space of algebraic curves, we know that we need punctures. We need to consider puncture curves. And what happens is that in the supersymmetric case, one has two kinds of punctures. The punctures which are not mentioned here, which are just punctures in the underlying curve, they are called by physicists Neveu-Schwarz punctures, which means something which are not going into. But it's also possible to consider a different kind of punctures, and they are called Ramon-Ramon or simply Ramon punctures. And basically what happens is that a supersymmetric curve with punctures, with Ramon punctures, is not a supersymmetric curve because you modify the definition. And actually what you want to have is some divisor, superdivisor Z here, whose ideal is an even line bundle. And then you want this to be finite and flat over the parameter space. And then the superconformal structure now doesn't square to theta mod D, but rather to theta mod D twisted by minus Z. So this is a true supersymmetric structure away from the divisor Z in a sense. No? Okay, these are called Ramon punctures. They appear in a natural way in the application of supersymmetric curves to string theory. And in the particular, we're talking about a divisor Z, which will have irreducible prime components, and we call them indeed the Ramon punctures. Then a work that I did with Daniel was the following. Actually, the modular space of supersymmetric curves without punctures was constructed many, many years ago by Lebrun and Rothstein. I think back in 1988, if I remember well. If you want to add Neveu-Schwarz punctures, it's very easy. It's nothing more than what you do with ordinary algebraic curves. If you add Ramon punctures, is slightly more complicated. And then it was a good opportunity to write a paper with Daniel. We did that back in 2021. So the first work we did in this topic was to construct a modular stack of supersymmetric curve with Ramon punctures, and also a Neveu-Schwarz. Here they are not included, but you may easily include them. Now, here I wrote algebraic superspace. I also said stack. Now, from this point, I'm going to use the terminology stack. In particular, I want to consider superstacks. Now, I don't think I have time to give a short introduction to stacks because that would, I would need the entire time that is left to me in this talk. So I could do some hand waving. So, for instance, we could say that stack, let's not talk about superstacks for a moment, but a stack is the algebraic geometric analog of what in differential geometry is an orbifold. Could be more technically, it is a pre-stack is a category fiber in groupoids over a site. Site is a category with a Grothendieck topology. So you have a category with a Grothendieck topology, and you consider another category which has a functor going to the site, which makes this a category fibered in groupoids. Namely, the fibers of this functor, which is the projection of the family, are groupoids. This is a pre-stack, and then a stack is a pre-stack which satisfies descent. The descent condition means technically that all descent data are effective. This means that you can glue things. So if you have objects in your category that satisfy gluing conditions, then they glue. Basically, this very hand-waving, of course, definition of what a stack is. A pre-stack is a category fiber in groupoids over a site, and the stack is a pre-stack which satisfies descent. Okay.
Sorry, one question. The assumption G greater or equal than 2 can be relaxed if you take more than enough points.
Yeah. This was just to write a formula which is true. Yeah.
If n is big enough, then you can...
Yeah, but by the way, if you if you work with the stacks, you can even write this in general, and accepting that the stack may have a negative dimension. So no problem.
But if n is big enough, then you have a positive dimension.
Yeah, exactly. Yeah, the formula is the same, and the dimension even dimension may go down, and also the odd dimension. The even dimension in particular may go down to -3, no problem. I mean, stacks may have a negative dimension. Okay, in algebra, so you see, if you consider stacks, you have a nicer stacks, which you call algebraic stacks. You have even nicer stacks that you call the limban for the stacks, and you have even nicer objects that you call algebraic superspaces. So the structure is more and more, I mean, you require more and more things, and you obtain simpler objects in a way. This is an algebraic superspace, which in particular is the limban for the stack, superstack, I mean. You see, the fact is the following, that the standard in algebraic geometry, the standard site that you consider when you speak about stacks is the site of superschemes, the category of schemes, sorry, with the étale topology. But the definition of stacks is so general that to say what a superstack is just enough to replace the site of schemes with the site of superschemes with étale topology. You apply the standard definition of a stack and you get what you call a superstack. There is really nothing to do. The theory is so general from a categorical viewpoint that immediately adapts to the setting of supergeometry. So we may talk of superstack with a light heart because there is really nothing more than stacks just by choosing in a suitable way the base site, the top category with Grothendieck topology. In this case is superschemes with étale topology. The genus is the genus of the underlying curve. As any superscheme, a supersymmetric curve is an underlying ordinary scheme, which is, in this case, an algebraic curve, and G is its genus. Okay, then you know that to do nice modular spaces of curves, you need a stability condition, no? Stability condition means that you want to kill automorphisms, and then you consider nodal curves, which may be reducible, and you ask that every rational component has at least 3 punctures, etc., etc. So there is a well-established theory of what a stable curve is. Basically, when you have a supersymmetric curves, you basically you say that a supersymmetric curve is stable when the underlying curve, ordinary curve, is stable. So there is really nothing deep in the notion of stability for a supercurve. Here is a little more complicated because we consider the Ramon punctures, but really Ramon punctures produce ordinary punctures for the underlying curve. You should take them into account, and you get a notion of stability. Okay, and then here I already basically told what is written in this slide. So let's just remind that a superstack will be a stack over the étale site of superschemes. That's a category fibered in groupoids over the category of superschemes equipped with étale topology satisfying the descent condition. Then we have here, I will use the notion of representable morphism, and let me just say what it is on the blackboard. So suppose that you have a morphism of Priest-X. Then first you say what a schematic morphism of Priest-X is. You ask the following, that whenever you have here a map, so these are two Priest-X. Here you have a schema. You have a map to Y, and then you take the fiber product. You want this to be a schema. Well, this means the following, that if you have a schema X over S, this will give a stack which is defined in the following way. Okay, this makes a stack, a schema into a stack. So when you say that if you take this fiber product, you get a schema, it means that the stack that you get as a fiber product actually comes from a schema. In this sense, you say that a morphism of a Priest-X is a schematic. Then you use this to define what an algebraic, let me check, I want to be sure to write it correctly. You use this to say what an algebraic space is. So if you have a stack over the entire site of schemes, I say this thing in the ordinary case, in the super case it's the same. Okay, so I can just stick with the usual notations, notion. You say that this is an algebraic space if there exists a morphism from a schema which is it is a schematic et al. Surjective. So this is what an algebraic space is. And then you say that a stack X is algebraic. No, sorry. First I need, we had a definition of schematic morphism. Now that we know what an algebraic space is, we can say what a morphism of a representable morphism of Priest-X is. We want the existence of a scheme with a morphism such that when you take the fiber product, this is an algebraic space. So it's a kind of a second step definition of schematic. First, you define schematic to define algebraic spaces, and then you say that a morphism of Priest-X is representable if this happens. No? When you must have a morphism from a scheme such that when you take a fiber product, you obtain an algebraic space. And then finally, you have a definition. A stack X is either algebraic or the Lee-Mumford if there exists a morphism from a scheme which is representable surjective, and then it's either smooth if you want the stack to be algebraic, or étale if you want the stack to be the Lie-Mumford. Anyway, you have definitions. Okay. I felt a little uneasy to use this terminology without at least defining it. This is what you have, which is also written in the slide. So in the super case, it's exactly the same stuff, but here you write, you consider the category of super schemes. Okay, I see that time is running, as usual. So work has been done by Felder, Kasdan, Polishuk, for instance, considering stable supersymmetric curves. So they prove that the stack that you get a stack, super stack, which is the Lie-Mumford. And we use this result, so a previous result by Felder, Kasdan, Polishuk. The modular space of stable supersymmetric curves is actually smooth. Not only it's the Lie-Mumford superstack, but it's also smooth. You have a good notion of smoothness for a stack. I think I have to skip this because I want to go to stable supermaps. And you know, when you have, in the ordinary case, you fix so if you want to have stable maps, you fix, say, a projective variety, and then you study maps. You study basically, you fix, well, something which may be, you may think of it as a class in the first child group, and then you consider pairs, CF, where C is a curve, an algebraic curve, and F is a map from C to X with the property that the class of the image of F in X is beta. Okay? Beta is the degree of the map, no? And in this sense. And then you parameterize these things, a modular natural notion of isomorphism. You can add punctures, and you have a stability condition, which basically is that those curves whose image in X is a point must be stable. Okay? So the curves that are contracted are stable in the sense of ordinary, of algebraic curves. Okay. So you see, you need to fix the cycle beta, and then if you want to do this in supergeometry, we need a theory of supercycles, which is not easy at all, and we were able with Daniel to develop it only up to a point, but a point which is enough to state the definition of stable supermap. Basically because we are considering classes of curves, of stuff having even dimension 1. No, I think that the problem here is the odd dimension, having odd dimension 1. Anyway, don't have time to go through this. And then you define supermaps in the natural way. So you have, Well, here I did it slightly complicated. This is the analog of the PRCF I wrote there, but I also consider punctures, Neveu-Schwarz and Ramon. I considered the possibly twisted superconformal structure, which is given by this differential operator delta bar. Now you have stability, but anyway, you have the stuff. And okay, of course, this generalizes if even in the ordinary case, if X is a point, a stable map is a stable curve. No? So in this sense, stable maps generalize stable curves. And then the result we had recently, so we are talking about 2 preprints which are in the archive now. We proved that if the target, which I called Y here, not X, is a smooth projected superscheme, then we have a modular space of stable supermaps, which we proved is an algebraic superstack. And we are working on proving that it is a smooth Deligne-Mumford one. So I don't claim it is so far, I just say that I believe it is. Okay, and we are working on it. Smooth Deligne-Mumford superstack. It's a bosonic reduction. So in the same way as a superscheme is an underlying bosonic scheme, a superstack is an underlying ordinary stack. And if you take this superstack of stable supermaps, it has a bosonic underlying stack. And this is not, in the case of stable curves, the underlying ordinary stack is the stack of stable curves with a spin structure. Here, it's not true. This is a small thing that we were very surprised. But we have a confirmation of this, by the way, by the dimension formula I'm going to write in the last slide. The bosonic reduction of this superstack is not the stack of stable spin maps. So stable maps where the curve C is a spin structure, specified spin structure, but rather a vector bundle on it. Here, everything is the Deligne-Mumford. The stack of stable spin maps is the Deligne-Mumford. This is known from the literature. A vector bundle on it is still a Deligne-Mumford stack. So it's true that our superstack, which we believe is the Deligne-Mumford, has an underlying bosonic stack, which is the Deligne-Mumford. This is known. And here we are working, this time in collaboration with Andrea Ricolfi from SISSA and Emanuele Pavia, former SISSA postdoc now in Luxembourg. We are constructing a perfect obstruction theory for this superstack. Namely, I don't want to go into the details of what a perfect obstruction theory is anyway, it's a theory which has a byproduct, a deformation theory, a theory of finitesimal deformations for the superstack, and the construction of a virtual fundamental class, which as a next step would allow to define Gromov-Witten invariants in this setting. So super Gromov-Witten invariants. So this is something we are working on. We already have quite a lot of work done, but not yet finished. Now, if we had all this, if we had all this, I mean, the perfect obstruction theory, we would have deformation theory, we would be able to compute the dimension of this superstack. Okay, we computed the dimension even without having the perfect obstruction theory, simply applying a superversion of the Grotadí-Riemann-Roch theorem, which is due to Mandini-Penko-Voronov, quite old stuff, by guessing what is the complex which governs the infinitesimal deformation. It's very easy to make a guess. Okay, and I'm just applying that guess. Okay, so the infinitesimal deformation theory is still missing, but we made a guess. The guess is very natural. And so we computed the dimension, and I split, just for convenience, the even and the odd dimension. So I called it the virtual dimension because this is going to be a virtual dimension, because this object will not have a dimension in an ordinary sense. And you see, for instance, that if you consider the even dimension, this is the dimension of the underlying ordinary stack. The yellow part is the dimension of the stack of stable spin maps. Completely classical object, but you see that we have this pink stuff in addition, and this is exactly what you expect from this result, because the bosonic underlying stack is not the stack of stable spin map, but it's a vector bundle on it. So the pink stuff is the rank of that vector bundle. So, and by the way, we made, we studied the particular case when Y is a projected superspace and everything fits. So once we shall have a deformation theory, hopefully this will be a theorem. It's not for the moment, but anyway, so that's all. I thank you very much for your patience.